All right, so we're going to start chapter one, and as I said in the syllabus, is about computer abstractions and technology. So let's just jump right into it. What do we mean by abstraction? Why is it so necessary for a course like this in computer architecture? So as I said in the introduction and the syllabus, the course is about essentially how to design processor chips. And is relevant to really designing any type of complex digital systems which are expressed or built as chips. It doesn't have to be a microprocessor or a microcontroller, even some other type of complex digital system. It could be a graphic processor. It could be a specific AI inference engine, for example. Some other type of a specific chip that has complexity. How do we get around to understanding and putting it together at what level? Now, specifically for microcontrollers, for processors, microprocessors, uh, we have defined an interface, very important abstraction, which is called the instruction set architecture. A lot of this chapter and the course is devoted to developing that understanding. It's really a contract between the designer, the developer of a processor, and the user. And as I said, the user is really the person designing that compiler because the end user is going to be programming in a high level language. So it really doesn't care how that processor does what it does because it's so far removed from a high level construct of a C++ or a Python type of syntax. But at some point, what is actually doing the work is at the level of the bottom is transistors. Transistors that are really behaving like switches and turning on and off and giving us those ones and zeros. So at some point, that high level gets translated to the specific syntax and understanding and language of that particular processor. And that application is called a compiler or an interpreter. So Python is interpreted. So it's someone needs to understand the specifics of that processor so that she can write that compiler. And that understanding is the instruction set architecture. It's the group of actual processor specific instructions that is what the processor can do. An example, it may be that you have a processor that doesn't have a, let's say, a divider. It doesn't have hardware to do division. It doesn't have that piece of hardware. Or it may be that it doesn't have the hardware to do logarithmic or trigonometric functions. It doesn't have the hardware to do floating point. It can only do fixed point type of arithmetic. But it's still, you could do floating point if you use the fixed point to do floating point algorithmically. Well, the compiler person has to know all that, has to know exactly what is it that the collection of real instructions at the processor level that this system can do. So that's that interface. So here we have on top of that instruction set the assembler, and the operating system also has to know about the processor because it's a facilitator. For example, the file system needs to know what is the width of the address bus, memory, the address space, and things like that. So, but the assembler is the one that actually translates directly into the native instructions of that processor. And on top of that assembler, there is a compiler that may translate a high-level language to some type of intermediate format, some algebraic syntax. But these days, these two are really one and the same. Okay, and on top of all that, we have the applications. It could be a browser, it could be Word, it could be Excel. But this is that contract with the user. This is what the processor does. This is what the processor, how it handles I/O, interrupts, how it handles memory, the actual processor. And as long as this doesn't change, the user has a consistent view. The nice thing about this abstraction, the instruction set architecture, is that you can have one interface here, but you could, as we'll see, and we'll see that in chapter 4, you can have different implementations where you can make trade-offs of cost versus the speed and performance without changing that abstraction. So as far as the user, you may have different implementations of all this, but nothing has changed. So that's very nice, because this is a big investment over here. Okay? So, and the processor is built with data path and control. We'll see what that is specifically. And those are blocks that are really built with digital design, right? So we have gates that make up these blocks, and the gates are made with transistors, circuits of transistors. So a NAND gate takes, a 2-input NAND gate takes 4 transistors. A 8-input OR gate takes 16 transistors. So, and so on. So, we don't want to understand or try to understand the complexity over here at this level, or even at this level so much. So we'll stay around this level here, but with a consistent view of that instruction set architecture. So that is so important. That's going to be a big part of the course. Now the course is called Computer Architecture and Organization. So let's make a distinction of those two. What is architecture? So architecture, again, is what is visible to that client programmer. Things like the actual instructions. How do we represent data? How do we use those bits? What are the I/O mechanisms? Different addressing modes, addressing techniques. We'll see what that means. And a little bit of an advance is that in a course like this, and to teach a course like this, what works is not to talk 100% in generalities, but to pick an example. Let's say an example ISA or instruction set architecture, and go through it. So we're going to be talking about the ARM instruction set, but everything that we talk about generally will translate to other instruction sets, like the x86, the Intel x86 family. So, but you have to have an example. Now ARM, as we'll discuss later on, is the most popular ISA because it's widely used in embedded systems that surpasses the number of, from an install base perspective, surpasses any type of PC numbers in the world, mainly because of cell phones. Okay, so ARM is a good choice. We'll be using that. So architecture are your way of communicating the capabilities of that processor to the user in a consistent way. Is there a multiply instruction, as I mentioned, or a divide instruction? You don't need that piece of hardware from an instruction perspective to be able to do multiply, because you could do it with adds and shifts. It takes longer, but you still can do it. Just like you don't have to have a floating point unit to do floating point. You don't even have to have 32 bits to do floating point, which is in single precision is 32 bits. You could do it with 8 bits. It takes a long time, but you can do it. That's architecture, that type of communication. Organization is how those features are implemented. What type of control signals, the actual interfaces, the memory technology. Are we going to be using the hardware for the multiply? Are we going to have to be doing adds and shifts and just have some state machine that repeats and loops through the adds and shifts by repeating the addition? Or we're going to have a parallel multiplier which can do the multiplication instead of doing it by repeated addition in multiple clock cycles. This parallel multiplier could do it in a single cycle, but it's much more expensive in terms of hardware, in terms of number of transistors. That's a decision. Now, whether you do it in a single cycle with a hardware multiply unit, or it takes you 32 cycles to do a, let's say, a 32 by 32 bit multiplication, where you could have done it in one cycle, it takes, let's say, 32 cycles, you could implement it either way, and you can see the trade-off. One cycle, much more expensive in number of transistors or hardware. Repeated addition takes longer, but it's cheaper. To the user, is a multiply instruction. That user doesn't care if he doesn't care how long it takes. She just wants it done. Then it doesn't matter how long it takes, as long as it's there. That single multiply instruction could be implemented in two ways, two approaches, but to the user, it's just a single multiply instruction. That's the beauty of the instruction set architecture abstraction from the architecture perspective to the organization or implementation perspective. So we're going to be talking a lot about architecture in chapter 2. Chapter 4 is a lot about organization. So that's a big sort of dichotomy division. So this is just a summary of what we already talked about. But it's the formal definition introduced here. The ISA, or instruction set architecture, is the actual contract or specification that determines how a high-level language like C++ will interact with the actual processor. When we talk about computer in this course, most of the times we are talking about the processor, because the computer can be so heterogeneous. I mean, is it a cloud cluster, or is it a tablet, or is it a laptop or a desktop? They all have a processor at some level. So we're really talking about the CPU. So that determines that computational characteristics. Is that collection of the capabilities that have been implemented in the hardware by some hardware system architecture. Okay? How much cache does it have? How does it handle interrupts and I/O? And what are the actual implementations of the data path, the capabilities? We talked about multiplication. And turn on the lights here. and how the actual implementation of the data path and the control is organized. So, do we have a single cycle? Do we have a multi-cycle? Do we have a pipeline implementation? If we're doing, how we're doing instruction level parallelism? Are we doing superscalar, or are we doing a very long instruction word? We're going to be looking at all those ways of implementing things, which are issues of hardware systems architecture. That's in chapter 4. But you always have to keep in mind that no matter how we implement a specific architecture, the instruction set doesn't change. And that's a nice thing. And that's why you can, for example, you can actually take a compiled binary program from 1985 and run it on an Intel processor today. Why? Because the instruction set of Intel processors have been always superset. They're always a superset of before. They have carried all the previous instructions in the instruction set, and the same instructions that were there in 1985 are there today, and many more. But they are there, so you don't have to recompile. That was important to Intel, that you didn't have to recompile and the binary would run forever. It's a trade-off. It actually cost them to carry that, but that was important for them. But that's an example of the power of keeping true to the instruction set in processor design. There have been many different architectures throughout history, and architecture classifications, and also components, right? I mean, historically, back to one of the biggest, it was actually a very good computer, but it was huge. It was what was called a mainframe, where computers took a whole room, the IBM 360. And instruction sets and architectures, they evolve. Like I was talking about the Intel evolution, they have added instructions. So they have been an evolution and different classifications. We're going to be seeing, for example, von Neumann type classifications that refers to how the processor interacts with memory. So for von Neumann, both data and code reside on the same memory, actual memory block. There is another way of organizing that, where you separate code and data, and they don't share a memory bus. You have a dedicated bus for that interface between the processor and the code memory, and you have a separate interface for the memory that holds the data. That's called a Harvard organization. It's better because you don't have to share the bus, but it costs you to have a second bus. So that's a trade-off. The implementation also has choices. Again, parallelism in processors. We're going to talk about that in chapter 4. How to do the actual control. Microprogramming is one way in which actually each instruction is implemented by the hardware of the processor as a series of what is called micro instructions, which are not visible. They're not visible to the user They are just there to implement that instruction that is visible to the user. That's a way of doing control. Another one is what is called hardwire, which really is a state machine. So when you see hardwire call as a way of implementing control, you're talking about a state machine. However, it becomes very complex. Yeah, you have so many states that it becomes almost unmanageable. So at some point, you have to go to this micro program implementation. Front and center of the discussion of implementation of processors is the cost performance. That's always a trade-off that you're making, or used to be for a long time. And classically, cost performance, when we talk about cost, is the actual cost of the number of transistors that you occupy a physical area on the chip, real estate. And you can actually come up for a cost of how much that picoacre of silicon costs versus performance, which is really measured of, and we're going to see different ways of benchmarking that, but let's just say gigahertz of the frequency that the processor can run at. So classically, that has been the main trade-off. However, given the way and that we're using technology, there is another factor, right? And I hope that everybody can guess what it is. The other one is power, battery life. Because if you have something that is very inexpensive and high performance, but you have to charge it every 5 minutes, that's a non-starter. That's not a good product these days. So power is another dimension that has been added as in the last few years, quite a few years. Okay. Now the key here, if you take this as a summary of the distinction between architecture and organization, and what is in that middle, the instruction set architecture, is that one architecture can lead to any number of implementations. And the bridge, the contract between the architecture that is visible to the user and any of those implementations is the instruction set architecture abstraction, which defines the capabilities of the processor atomically at a instruction set level. Okay, so that's the summary. That's the main thing to understand. Okay, so I'm going to stop here because we have 5 minutes left, so I can go and check the chat box, see if anybody wrote any questions, and I will address those.